So allow me to share my screen. Okay, so hopefully everybody could see my screen. So we'll be now talking about a new topic still under the first order differential equations. This time we're going to talk about homogeneous differential equations. So in terms of comparing it with separable differential equations, in separable differential equations class, you are only comparing with the form of the differential equation, then you can classify it as separable differential equation. But when we speak of homogeneous differential equation, there has to be a test. We need to test first whether your DE is really homogeneous, because if it's not homogeneous, there's no point in having to solve it using the procedure in determining the solution for homogeneous differential equations. So as how we're going to test for homogeneity, or how we're going to know whether a function is homogeneous or not, so let's go first. We'll go to the first slide. Now, a function of x and y is said to be homogeneous of degree n if there exists a constant n, where n is a positive whole number, such that for every quantity r, variable or constant, you will have this corresponding relationship. Now, let me explain what you have here. So originally, you're given a function of x and y. This one tells you, as you could see here, that your x and y now are multiplied to a constant r, or to a variable r. So meaning, in your original function, you are to replace all your x and y variables by rx and ry. And check whether after you have factored out the common factor r raised to n, where n is any positive whole number, this f of x and y that is being multiplied to your r raised to n is still your original function before you have changed your variables x and y to rx and ry. If that would happen, that is the crude way of testing whether your function is homogeneous and of degree n. Now, to illustrate the application of this particular statement here, so let's have a specific example. Let's say you're given x squared plus 2xy plus y squared. This is your function of x and y. Now, as dictated here, you will change all the x and y to rx and ry respectively. So you change the x here to rx and square it. So this would be the resulting expression. You do the same for the x and y here. You change it to rx and ry, and you change the y here to ry. So this will be the corresponding product. Now, what will happen is, if you inspect, all your terms here have r squared as the common factor. So if you factor out r squared, you have x squared plus 2x plus y squared. And what is this? Actually, if you look closely, what you have in here is your original given function. So this one is your original given function. And you have this r raised to 2. So the exponent of the r tells you of the degree of this homogeneous function. We say homogeneous because after we have factored out the common factor r raised to 2, the terms that you have are exactly the same as the original. So we say it's homogeneous, and its degree is based on the number or the exponent of the r which you have factored out. What will happen, class, is if after you have factored out a common factor of r raised to a particular exponent, the expression resulting from the factoring is not exactly the same as the original, then we say that your function is non-homogeneous, because it will only be homogeneous if it's exactly the same as the original. And the degree would be the exponent of the r. Now, this entire thing, class, is the crude way of testing for homogeneity. And some of my students before would like to eliminate this part, but rather would go straight to inspection only of the degrees of each term. Now, you may ask, what do you mean, Miss Ali, with the degree of each term? In your algebra, when you speak of the degree, it's the sum of the exponents of the variables that appear in your particular term. So this one is 2. This one is 1 for the x and 1 for the y. So that would also be 2. And this one is 2. So even if you did not do this crude manner of testing for homogeneity, you can still say that your original function is homogeneous of degree 2 because the degrees of each of the terms are the same. So there's no need for you to do that. But if you really want to, in cases of functions which have transcendental functions, so what I mean with transcendental functions, functions that have sine, cosine, ln, exponential function, arc, tangent, something like that, then at times it's suggested that you really do the crude way of testing for homogeneity. But if it's just something like this with no transcendental functions present, you can right away tell whether the function is homogeneous or not. Now, if you go here to our second example, let's say we will not do the crude way of testing for homogeneity. You simply check the degree of each of the terms. So this is 4 plus 1 for the y, that's 5, and this one is 5. So automatically we can conclude that your second function is homogeneous of 5th degree. So homogeneous of 5th degree. Now it will only be homogeneous, again, let me emphasize this, if and only if after you have factored out the common factor r raised to a particular exponent, you still have the original function, or you go back to the original given function. Then it is homogeneous. Now, if it's not the same, then it is not homogeneous or non-homogeneous, and there's no point in having to solve your DE using the procedure for homogeneous differential equation. Now that you have already learned how to determine homogeneity of functions, now we will apply this concept to a particular differential equation, or we will apply it generically to a form of the differential equation. So the first order differential equation, m of x and y dx plus n of x and y dy equal to 0 is homogeneous. So now we're talking about the differential equation. If m and n are both homogeneous functions, so meaning m has to be homogeneous, n has to be homogeneous, how you tell for its homogeneity, it's the same as what we did in the previous page. And they have to have the same or equal degree. So they have to have the same degree, homogeneous and the same degree. Now question, what will happen if m and n are homogeneous but are not, excuse me, of the same degree? Then your differential equation is still non-homogeneous. So the requirement is 2. Both m and n has to be homogeneous and they have to have the same degree. Now let's look very closely to this given differential equation. The square root of x squared plus y squared plus y, quantity multiplied to dx plus x dy equal to 0. If you look very closely to the degree of the x and y variable here under the square root sign, it's squared. However, it's under the square root sign. So the square root sign is actually an exponent raised to 1/2. So if you have x squared raised to 1/2, the resulting degree of that is 1, right? 1. Now, that's for this particular term here. This is first degree. The y here is also first degree. So that tells you that the coefficient of the differential of x is homogeneous of first degree. Homogeneous in the sense that all the terms have the same degrees. Now, what about here? The second term, you have x dy. You have only x as the coefficient of the differential of y, and its degree is 1. Now, since the degree of n here is 1, and the degree of m here is 1, both are homogeneous, so we say our differential equation is homogeneous. So m is homogeneous of degree 1 and n is homogeneous of degree 1. Therefore, this particular differential equation is said to be homogeneous. Now, what will you do now if your DE is homogeneous? So that brings us to the procedure in finding the solution of a homogeneous differential equation. Now, before I go to that particular procedure, do you have any question here in the testing for homogeneity?
None, Miss.
Okay, none. Sige. So that is good. So let's move on. Now, in finding the solution of your homogeneous differential equation, it's a two-part solution. First, you establish the homogeneity, and the second, of course, you determine the solution. Why is it a two-part solution? Because you cannot go directly using the procedure for a homogeneous differential equation if in the first place your DE is not homogeneous. You will simply be wasting your time because what you're doing is wrong. So it's a requirement that you use only the procedure that I'm going to discuss to homogeneous differential equations. So now let's go to determining the solution. In determining the solution class of a homogeneous DE, it involves two options. Both options have 5 steps to follow. Actually, they are just the same. It just depends on the substitution equation that is being used. Now, let's go first to option 1. Then we go to option 2. The note that I have placed here is just a suggestion. It's a suggestion. If you don't feel comfortable with one suggestion, then you may opt to use any option that you like depending on the resulting expression that you need to integrate later on. Okay, so what is first option? First, we create a new variable b. So this variable, by the way, class, this b variable is arbitrary. So it could be any letter you like. We use the b variable here because it's the same variable that is being used in our general reference book, Elementary Differential Equations by Rainville and Bedian. So it's b. So b, what is this b? It's equal to y over x. So you use b equal to y over x if your differential equation has variables y and x. If your variable, for example, or the variables present in your DE are s and t, or w and y, this would also change because this one, the substitution equation is only for a differential equation which is said to be standard in the sense that the variables are x and y. So if it's not x and y, you can change this one. Anyway, when you got already the answer, like later on, you will substitute again what b represents to the original, so to the solution of that particular problem. Okay, so this is step 1. You use the substitution equation b is equal to y over x. And what are you going to do? Second step, you express y in terms of x. So meaning, when you use this substitution equation, all, as in all y that appears in your differential equation should be changed to vx. That even includes the y that appears in the derivative. So if you have y and x as your variable in your DE, then your derivative must be the common dy dx. So you see this y here, that should also be changed to vx. If we change the y to vx, as you could see here, you will perform product rule of differentiation in this part because you are to get the derivative of the product of vx. So your EMA 101 taught you how to do product rule of differentiation. First term times the derivative of the second plus the second times the derivative of the first with respect to dx, of course, because your denominator is the differential of x. In the process class, you get to cancel the dx here. And in this particular substitution equation, now your dy dx is equal to b plus x dv over dx. So the dy dx in your original DE should be replaced by this, and the y should be replaced by vx. So that would be now your step 4. Correspondingly, all y in the equation should be changed as well. Now, after you have done that, you will notice, class, this is based on my observation after like more than 20 years of teaching DE. you will notice that your homogeneous differential equation is transformed or converted to a separable differential equation when you do this procedure. So after integration, that is after separation of variables and integration, you need to replace all the v in your answer in the original solution by y over x. Because in the first place, that's where you started from. And another reason is your original DE does not contain a v variable. So, imposible man nga ang imo solution may v nga variable, kaya ang original mo nga DE wala v. So, you have to substitute or change all your v's in your solution to y over x. Now, option 2, the steps in option 2 is actually in principle the same as the steps in option 1, only that we change the substitution equation. In here, we change your v here is equal to x over y. Here, it's y over x. In the process, you have this corresponding expression. This time, it's not the y variable that you're going to change, but rather the x. So all the x variables that's present in your differential equation, you change to vy. So that includes the x in the differential of x. So if you change this x to vy, you again use product rule of differentiation. So first term times the derivative of the second plus the second times the derivative of the first. It's because this dx there is actually the d of vy. So you perform here product rule of differentiation, and this would be the resulting two terms. Now, in here, you have replaced all y's. In here, you will replace all x and dx in your original DE. After separation of variables and integration, you need to replace all the v's again in your solution to this time, not y over x, but x over y. Now, question, when will we use option 1 and option 2? This is a suggestion, okay? But some of you may like this better. Most of the time, my students would like this because the corresponding expression equivalent to dx is only having variables that does not contain fraction, where this one has. So they find it difficult to combine with other expressions which are not rational in form or are not in fraction form. So most of my students would use option 2, even if option 1 is also another option for them to use. So this is a suggestion. If the m of x and y is simpler in form, use the substitution equation x is equal to vy. If the coefficient of dx is simpler, I'm referring to m. But if it's the other way around, use the substitution equation y equal to bx. You will notice, class, that there will really be a great, shall I say, difference in the look of the solution from one option to another, but you will still come up with the same answer. But in terms of how the substitution equation for a particular option simplifies the, let's say, the part of integration or the part of separation of variables, you will see it later when we do a particular example using both options. So you could compare, ay, mas simple di siya gali kung amon ni compared to this one. So you will learn as you go along which of the two options is easier to perform. Okay, now we will proceed. So do you have any questions here before I clear my markings and go to the next page? Okay, so I take it that your silence means that it's clear for now. So we will proceed to the next page. Now, let's say you're given this particular differential equation. Now, I will do inspection, class. You see, this is second degree, this is second degree, and this is second degree. All the terms are in second degree. So if I don't use the crude way of testing for homogeneity, I can right away tell that this DE is homogeneous. Okay, it is homogeneous. As to whether it's exact, I will not tell you. I leave that to you to check whether it's separable. If it's not separable, then you go to the next. Is it homogeneous? Since your answer is yes, then you may use the procedure for determining the solution of a homogeneous differential equation. So we start with this rational expression that we have on the right, okay? We will simplify. There's no testing here anymore. I just simply tested using inspection, second degree, second degree, second degree. So homogeneous. Now, if we will simplify, we will distribute xy to x squared and y squared in the numerator. So this would be it. And you notice that this will cancel out, leaving 1 here. And this will cancel out, leaving 1 here, okay, as the exponent. So your first term now is x over y, and the second term is y over x. Now, we want to make both of these expressions similar in form in terms of what available expression we have in the two options. So if you go with the first option, that would be b is equal to y over x. So if you want to use that one, you may change this one. Since this is x over y, you may write it in its reciprocal. What does this mean? Actually, this one is 1 over y over x. So if you invert this one will go up. So it would be x over y, the original. Why write it in this form? So that they will look similar. You can represent them with the same variable. So we will now use the y over x. Okay, so you have here y over x, and that would be equal to b. You can see here. And I think this is the first option that we use. Y being equal to bx, or we say that b is equal to y over x if we transfer this x on the other side. Okay, now since I have already class simplified the right side in this form, now I copy the derivative here. I place it here. Okay. Then I will now do replacement. I'll replace my y with bx. So this y here will be changed to bx, and this is the corresponding equivalent expression which was shown to you in the previous page. Okay, previous slide. Now, if this one will be going to use this relationship, we know that b is y over x. So then this must be b raised to negative 1, and this one is b. Okay? Now, if you look intently on the corresponding equation that you have, the b on the left will get cancelled with the b on the right. So leaving you with x dv dx equal to b raised to negative 1. Okay? Excuse me. Okay, I have a grade 2 student here who is really uh, who opened the door, so I cannot concentrate. So let's go back class now. So we have now this particular expression. If you look closely, class, you notice that this is separable, as I have said. Separable in the sense I can place the v here together with this dv, and I can transfer the dx and the x on the right side. Let's see what it's going to yield. Okay, I clear all my markings and go to the next. Okay, so if we do that, this is the corresponding expression. This came from the dv with the v raised to negative 1 on the other side. So the v raised to negative 1 is actually 1 over v. So if you cross multiply, this is the corresponding expression. And this is your 1 over x dx. Okay, let me go back so you will see. This one actually, so the others may not be able to follow right away. This is 1 over v. So if you do cross multiplication, it gets to be transferred here. This one in here and the x below. Okay, so you can see here on the next slide the corresponding result of that. Okay, so you have this. Now you could see we have separated variables. So from a homogeneous differential equation, due to our substitution equation, we have transformed it into a separable dE. Using power rule, this will be the corresponding expression. So you have b squared over 2 equal to ln of x plus c. Okay, now since you have an ln here, and if you recall our discussion on separable differential equations, if you have an ln in your answer, your c should be represented also as in the form of an ln. So your c here was represented as an ln of k, or it could be ln of c as well. There's no problem with the c being kept. Anyway, both C and the K are arbitrary constant. Now, since all now, the terms on the right side are in ln, you can combine them into one ln expression. Now, the arguments of the two ln's are written as products. Okay? Okay, so you have this. Now, since B is not part of your original set of variables x and y, you have to change it to what it originally represents. So you have y over x. So we change b to y over x. So this b now will be y over x. And this is equal to plus minus the square root of 2 ln of kx. Now let me just annotate so I can clear the drawing here. Okay, so if we simplify class, you cross multiply x on the other side. So I said cross multiply, not add. So you cross multiply, so it will be now plus minus x square root of 2 ln of kx. Now don't write the x class, don't write the x here when you do cross multiplication. Because if you do that, it would be interpreted as x plus minus the square root of this expression. But since when you cross multiply, you are actually multiplying, then the x should be multiplied to this one. And this, the sign of positive and negative written before it. Okay, so now if you look closely, this is now the solution of our homogeneous differential equation using the first option, wherein we have y is equal to bx. Okay? Any questions so far before I go to another example? Okay, there's none. So we will proceed. So let me just clear my markings here. Okay, in here, I have another example, but I have solved both examples. So both examples will solve using the two options so that you can compare which of the two options makes things easier. Okay, and in here, you would notice that also you will review a lot on the process of evaluating the integral expression. So let's say we look at this now. This is second degree in x. This is second degree in y. And this is second degree in both x and y. So without having to test crudely, we can say that this differential equation is homogeneous. Okay. Now let's say we use option 2. This is option 2. X is equal to by. Now, if we use this one, easy ang iya nga differential nga substitution because you don't see any rational expression here. So we change the differential of x in our original dE by v dy plus y dv. Why? Because, okay, so we will have, I'll annotate here. We have dx equal to d of vy. We use product rule here. So first term times the derivative of the second plus the second times the derivative of the first. Okay, this will be your corresponding substitution equation for the differential of x. So let me just close this so you can see everything. So now in your original dE, this one, you will change all the x to by. So this is now by squared plus 2y squared. The dx here will be changed to b dv plus y dv. The x here will be changed to by. The y you copy, and then the dy you copy as well. The rest is your algebra doing the thing for you because there's a need for you to do expansion here. You have to multiply these two binomials, yielding this particular expression, 1, 2, 3, 4. This one will yield by squared dy. So since it's on the right side, if you transfer it on the left, that would be negative. Okay? Now, in this side, on the other hand, the next thing that you're going to do, and by the way, class, you may wonder why, excuse me, class, Now, you have to transfer the dy here on the left side because you want to group the terms that have the same differentials. So you have here this term here that has the dy, and you have this term here that has the dy, and this one that you transferred on the left also has the dy. So you have to set the right side equal to 0 with the sole purpose of grouping all terms that have the same differentials. So in that way, you'll be able to see that the terms that has the dy has the common factor y squared after simplifying, because I think this one will be combined with this, giving you a by squared dy. So that is why you only have two terms here. So resulting to an expression b cubed plus b, the quantity of these two multiplied to y squared dy. The other remaining expression has dv as the common differential. So you factor out the dv and the common factor y as well. So that will now be multiplying the y dv to the quantity b squared plus 2. Now let me continue. Sorry about those short interruptions. So now you could see that there is now a separable. I will just clear the markings here. So you can see that you have here b variable, and you have y here, and you have dv here. So there's a need for you actually to get rid of this y in here. That way you can integrate this expression. In here, you have a b cube and a b, and you have a dy here. So there's a need for you to get rid of this entire expression of the b, because you should be having the dy instead for this particular term to be integrable. So how do we eliminate the v cube plus b and the y on this side or on this particular term? You can do that by dividing your original DE by the product of the two. So you have b cubed plus b, and you have the y. If you do that, class, what happens? The dy now here on the first term will be divided by y, and the dv on the second term will be divided by b cubed plus b. This particular b squared plus 2 remains because anyhow it's with the dv. Okay, so quantity b squared plus 2 dv divided by b cubed plus b. Okay, so from our homogeneous differential equation, what we have now is a separable differential equation which you can integrate. Okay, you can do integration. This one, I'm sure you will be able to tell that this will just yield an ln. However, for this one, you need to separate the two terms in the numerator by dividing it with b cubed and b. So you have b squared divided by b cubed plus b, and you have here 2db divided by b cubed plus b. Now, the rest of this class actually is your integral calculus already. This one is just an ln. However, this one will require that you use trigonometric substitution. Okay. Now, whenever you have this particular instance in which the integral expressions to be evaluated is quite difficult already to handle in terms of the requirement for recall of your previously learned techniques in calculus, you may change to option, to a different option. But if you intend to really use or to complete your solution staying on that particular option, then you may do so. So in here, if you use trigonometric substitution class, you first simplify the denominator. So your denominator here will be b times b squared plus 1. That would be equivalent to this. And you use this trigonometric substitution. B is equal to the tangent of x. And if we differentiate this, that would be dv being equal to the second squared of theta d theta. Now, what will you do with this 2? You substitute it in your original integral. So this is now second squared theta d theta for dv, and your v is tangent theta. This one is tangent squared theta plus 1. Your tangent squared theta plus 1 is equivalent to secant squared theta. So you get to cancel the 2. Your tangent is sine over cosine, so the cosine goes up in the numerator and you have sine theta in the denominator. This one yields an ln. Okay? Now, but what is this theta? You don't have theta in your original DE. What you have is x and y. So you go back to your substitution equation, and I hope you can still recall, you construct the triangle. If B is equal to the tangent of theta, then it is having B on the opposite side and 1 on the adjacent side, because this is understood to be B over 1. So opposite over the adjacent is equal to the tangent. So the hypotenuse of this right triangle is 1 squared plus B squared, or that would be 1 plus B squared. So if it's the sine that we want, then your sine theta based on this particular right triangle is opposite B over the square root of 1 plus B squared, opposite over the hypotenuse. Okay, so you have this one now. Ln of y for this, and the corresponding expression for, wait class, the corresponding expression for the ln of, why do I have here a 1/2? By the way, class, this 1/2 ln of the quantity b squared plus 1 is for this. Okay? And you have this for the ln of sine theta. So you have 2 ln of b, as you could see here, 1 plus b squared under the square of sine. This one, this particular term here is for this one. Okay? You have now 2 here, and you have here 1/2 ln of b squared plus 1. Now, by the way, class, this one, the v squared over v cubed plus b will be actually yielding an ln. Why? Because, simplify here. Diri na lang ko, class, na simplify, ha? If you will factor out the v there, I'm talking about the second term. So you have v squared dv over b times b squared plus 1. You can cancel out one of the b's here. This will give you v raised to 1. Your integral now, class, is simplified into b dv over b squared plus 1, which will yield an ln if you have placed a 2 here and you place a 1/2 here, because this is now your u and this is your du on top. So du over u will yield an ln, so that is why you have 1/2 ln of b squared plus 1. This one is for this rather trigonometric substitution is for the third integral. This one, when simplified, will be this, yielding an ln. Okay? This, when simplified, would yield this one, yielding your ln, the second term here. This one will be using the substitution equation. The substitution equation would still be requiring that you factor out the v in here. That is why you have here the tangent. You have the b in here, and you have b squared plus 1 in here. Your numerator is just the dv, so that is why you have secant squared theta d theta. Okay? Now, I'd like to close this part here so you will see your answer later on. So if you have this as the 3 corresponding ln answers for this particular 2 sets of integral, the right side will be an ln of c. Everything is in ln. So if it's an addition thing, you are going to multiply everything. So this one, this ln of the square root of b squared plus 1, which has this one, 1 plus b squared, and this is also in ln, class, you need to subtract the exponent of this b squared plus 1, which is 1/2, from this. That leaves you with another b squared plus 1 in here, because you only took the 1/2. So there's a remaining 1/2. So that explains you have why you have here b squared and you have here y These two are being added. So the arguments y, let me annotate. The argument y here and b squared here is in the numerator. And this one, the square root, because of this 1/2 which you subtracted from the one exponent here is this one. Why do you have, you may ask, Miss Ali, why do you have a C na lang dire? Wala naman ln yan nabilin. So using the properties of ln that you have used in your, you have encountered and used in your differential calculus, whenever you have ln's added, it's multiplication. And when you have ln on both sides, you may raise your equation. Everything in your equation could be raised to the exponent of the e, eliminating the ln. So this is your corresponding expression. Now, the C here, actually, everything here is raised to E. Not raised to E, but rather made as an exponent of the E. The same thing in here when simplified already. So that is why you have left here a C. And this C here is this C in here. And you have this 3 in here simplified in this form. Now, since your original DE does not have a B, you only have X and Y, this B here that you have should be changed to X over Y. This B should be changed to X over Y. So if I close here with the annotation, the B is equal to X over Y. So tanan na din nga B is lang yung mansang X over Y. This B should be changed to X over Y and it's squared. So that is why it's also being squared. And this is your Y. The other side, the C times the square root of 1 plus B squared. So it would be C square root of 1 plus X squared over Y squared for the B. Okay, simplifying, this is the solution of your DE. Okay, now this is the solution of your DE using option 2. Okay, you used option 2. Primarily, why did you use option 2? Because my students would say, Miss, it's easier because in terms of the substitution equation that replaces the differential, it's not a fraction form, so it's easy. But look at the process of integration. It's very complicated already. It requires you to recall your previously learned principles. What if you use the first one, option 1, where y is equal to bx? I just changed the v here to u because we already used the v in here. Look at the process. It's very short. So the manner of determining what substitution equation you use will actually determine whether you will have an easier integral to evaluate or not. So in this case, if you use the option 1, the first option, though in terms of the substitution for the derivative, it's quite complicated, but this time, look, your solution is still the same as this one. This is using the first substitution equation. This one is using the second. So now you will have something to compare. So you may say, how do we know, Miss Ali, which one to use? And as I said a while ago when I was doing this part in here, once you already see that your integral is quite difficult to evaluate, try the next option. Maybe it's simpler compared to the option that you chose in the first place. So as to the clear-cut way of checking which one would lead to an easier process of determining the solution of a homogeneous differential equation, it's really based on practice and experience and exposure to handling homogeneous differential equation. Now, kay kung basihan taman ng aton dala nga suggestion for which of the substitution equation to use, in here we could see that the n is simpler compared to the m. So that is why the substitution equation that was used is the second option. But look, it's very difficult in here. But if you use the first option, this is the process of finding the solution. Okay, I'm now ready for your questions, your clarification regarding this particular process of finding the solution of a homogeneous DE. I'm sure you will say that the first example is easier. This one is not because I've used an option that lead to a difficult integral to evaluate. If I use an option that is leading to this one, then you will say, oh, it's easy because the procedure is short. So what really determines whether the procedure is short or not It's really you. It's dependent on the user, whether you'd like to stick on the original option that you have used, or you want to change gears right away because you saw that, oh my integral expressions are already complicated for me to evaluate. Are there any questions here? Which part in here you would like to ask questions? They say if there aren't any question, it's either everything is clear or everything is so hard to follow. I hope it's the first case. It's the first scenario in your case. Do you follow everything in here? Just stick to the procedure, class, the procedure. Use the substitution equation. Substitute the substitution equation to your DE. Then after you get the answer, after you have simplified, return the original variables in your DE by changing the V's, the V that appears in your solution, or changing the U that appears in your solution. By the way, class, it's just a V here, and it's just a U here. You can also make B, another B in here if you want. I just changed it to a U because I used the B already in here. Any questions? None? Okay, I'll stop sharing. Okay, I'll stop recording now. By the way, class, before I stop recording, can you please write your name in the chat box with the present word after your name? That way I can account for the attendance while waiting for the others to think which part of the solution they like to be clarified with. Write your name in the chat box and then beside your name present, the word present. Okay, so far we have Gonzaga, Mijares, Tison, Dichon, Maringa, Mercado, Piamonte, Esparagosa, Cedeño, Fernandez, Dunio, Durain, Durin, Trifalgar, Baisa, Magupoy, Boyson de los Santos, there's only 26 of you. I'm not sure if this is okay. So some are delayed. Okay. Okay. So since I'm still recording, so I can check the attendance in here. Okay. So I'll stop recording now.